Welcome back. So we start today's afternoon session with a talk of Nguyen from ICTS in Vietnam. Thank you, Dung, for coming to the meeting, and please, so we're looking forward.
So firstly, I would like to thank the organizer for invitation. So in my talk, I will show you that in the theme of the generalized symmetry, fractional quantum Hall actually have an anomaly, but I do not concentrate on this part. I only concentrate on the generalized symmetry of fractional quantum Hall. So in the limit called the lowest Landau level limit, fractional quantum Hall enjoy higher rank symmetry, and actually it's a nonlinear higher rank symmetry. And from this symmetry, there's some interesting consequence of that. So let me begin with the plan. So here I show you that the area-persevering diff is a symmetry in the lowest Landau level. It's considered as a higher rank symmetry, nonlinear higher rank symmetry. And I show you how to derive this symmetry in the lowest Landau level explicitly. And also I can also set the area-persevering diff in the lowest Landau level. It's a long wavelength limit of the W infinity symmetry, which is a famous symmetry in string theory. So let's begin with the first part. So here I just warm up to remind you about higher rank symmetry in the symmetric tensor gauge language. So here I introduce symmetric tensor rank 2 tensor case, and there is a canonical conjugate. So with this commutation relation, and we also need to impose the Gauss law for the higher rank symmetry, this Gauss law. Furthermore, the symmetry of the lowest Landau level also requires the traceless of the electric tensor. And with this commutation relation and this Gauss transformation implies the transformation of the gauge field under the gauge transformation. These two gauge transformations, first of all, come from the constraint, the Gauss law constraint, and second is come from the traceless constraint. So from these two constraints and the commutation relation, you can get the gauge transformation of symmetric tensor gauge. And with this two constraints implies the conservation law of the charge density, the dipole, the total dipole, the total charge, the total dipole, and here's the tray of the quadruple. This comes from this constraint. So now we can fix the gauge. We can use one of the gauge transformation here to fix Aij and make it become traceless. So AII and EII equal to 0 as a second class constraint because they have non-zero commutation with each other. From that, we can fix the gauge and we derive the new commutation relation after you fix the Dirac. We find the Dirac bracket is useful. D here is the dimension of the space. So with the new commutation relation, it generates a new, the Gauss law generates a new gauge transformation, the residual gauge transformation. And to construct the gauge invariant electric field, we need to introduce I0. And this form is invariant under the gauge transformation of Aij with the gauge transformation of I0. It's very similar to the Maxwell theory when you need to have the I0 and AI to define the gauge invariant electric field. So here is similar for the symmetric tensor gauge. Furthermore, with this gauge transformation, we can introduce a gauge invariant magnetic field. And then there's some gauge invariant Lagrangian that we can write down. The first one is the Maxwell, because the theory is non-relativistic, so the coefficients C1 and C2 not need to be related to each other. But here is the simplest form of the symmetric tensor gauge theory that satisfies the gauge invariant. The second one is the Chern-Simon theory for the symmetric tensor gauge. So I0 here is the same as before. H here is the magnetic field, and here is another term. So if we consider the matter field coupled with the background gauge field, because of the gauge transformation, we have this conservation law. So Jij here is the symmetric tensor current. And this shows you some like factonic behavior. So because of the conservation of the dipole moment, then the charge cannot move because the moving of the charge equal to create a dipole. And furthermore, the chase length of the symmetric current also tell you that the chase of the quadrupole moment need to be conserved. So that means the dipole moment can only move perpendicular to this dipole vector. Yes. So this paper discusses the Chern-Simon. So here now I try to convey that the Chern-Simon scalar charge theory in 2+1 be think of as a linearized version of area-preserving diff. So here I introduce the field Sij is the same as Aij, but there is some like relation. And from this explicit form, Sij is symmetric and chaseless also. So the gauge transformation of Sij, you just get the transformation of Aij to get the transformation of Sij with this form. So now if you consider Sij as the perturbation of the matrix, is this which following form? Delta Ij is a connector. And Sij is the perturbation of the matrix on top of a flat matrix. And then this gauge transformation gives you the transformation of the matrix. So it's nothing but it's a linearized version of the area-preserving diffeomorphism. So at this moment, I show you that's equivalent between the symmetric tensor gauge and the area-preserving diffeomorphism at linearized level. So if you want to do like nonlinear level, we need to promote the transformation of the matrix. Now I have the nonlinear term also. It's the same area preserving, but I promote this to the nonlinear, the full nonlinear transformation of the matrix under the diffeomorphism. And this, the transformation of the matrix, satisfies the area preserving algebra in the 2+1 dimension. So linear here, you're saying that 8 is small, and then I ignore the term like 8 multiplied by C and etc. But this thing is the full nonlinear transformation if you do the area preserving diff in GR, same form. So yeah, so you can do this transformation twice and do the commutator and see that we have the algebra. So that means the alpha beta here is a function, is a generator function of the diff parameter. And the commutation relation of these two transformations equal to another area preserving transformation, but with the generating function is like Poisson bracket of two functions. And then now I have the nonlinear transformation of the matrix. If I want to have a nonlinear transformation of the background A0, I also need to promote the transformation for the A0. And actually in fractional quantum Hall, we will see later that this is a transformation of the background matrix, and this thing is a transformation of the background scalar potential after you do U1 gauge transformation plus diffeomorphism. So this symmetry, you can derive this in in fractional quantum Hall. We will show later that it's identical. Any question? Yeah. Yeah, I think side pause. Yeah, side pause. So basically, we show at the end we can show that the transformation here and here it corresponds to the transformation in the fractional quantum Hall with a constant magnetic field, such that the L here is a magnetic length, and this transformation equal to Diffeomorphism transformation and U1 gauge transformation in fractional quantum Hall, and you get the same form in lowest Landau level only. Takes the massless limit. Yeah, so here now I try to show that the lowest Landau level has this symmetry. So we consider Z is a Lagrangian of electron in magnetic field. Yeah, this kind of line, the interaction term, but the kinetic term is here. So you see that as talked by Inti, we know the cyclotron frequency equal to B divided by M. So the distance between the Landau level is B divided by M. So when you take the M go to zero limit, or you take the B go to infinity, or M go to zero limit, we go to the lowest Landau level limit where we can zoom in a single Landau level and forget about very far Landau level. So it's a mathematical way to take the lowest Landau level limit. Okay. So if we take like change the variable of the coordinate with this one, we can write down the Lagrangian of the electron in the magnetic field with this form. So if you integrate out chi from here, you can come back to this Hamiltonian. You also have a Chandonovich transformation to get you back and forth between two Lagrangian. But in the lowest Landau level limit, when you take M go to zero, after you do the Hubbard-Chandonovich transformation, you can remove this term. So now chi now plays a role of the Lagrange multiplier, implying the lowest Landau level constraint. So dz bar icon per psi equal to 0 on dz icon per psi dagger equal to 0 is the lowest Landau level constraint that comes from taking the lowest Landau level limit by take M go to 0. So M go to 0, we have the lowest Landau level constraint on the electron field. Right. So now I want to discuss about the symmetry, the global symmetry of the lowest Landau level. Yeah. So I just use A and A dagger just for notation. And we use the symmetrical guys. So the global U1 is the symmetry of the problem. So you change the phi of the lowest Landau level electron field by global phi is the symmetry. And the consequence is the conservation of the total charge. Furthermore, the thing called the magnetic translation is also the symmetry of the problem. So if you just shift the coordinate with the constant, it's not the lowest Landau level, because if you just shift the coordinate, then the lowest Landau level constraint do not satisfy. You need to multiply this with some phase. And with this transformation, the electron field stay in the lowest Landau level. And you can write down the magnetic translation operator in terms of B and B dagger operator. That's staying in the lowest Landau level. And Z is nothing but is a magnetic translation operator. So Z is the full of the operator that do the magnetic translation. And then from that, you can have the Noether chart for this magnetic translation operator. Same with the B and B dagger here. And then you use the lowest Landau level constraint to chain of that. And then basically Z, iterate Z multiplied by rho and iterate Z band multiplied by rho and the conservation. So that is a microscopic way to derive the conservation of dipole moment. So we have the conservation of charge and conservation of dipole moment. Furthermore, you can have the magnetic rotation. So you rotate the coordinate with some phase. You rotate, global rotation. And this is the operator do this rotation. And it equal to B dagger B minus I dagger I. So when you sandwich the J, Z with the per side dagger per side, and using this constraint is the lowest lambda level, you can show that the angular momentum has this form. So the one here just comes from the A dagger I. So A dagger I act on the lowest lambda level, give you just 1. But B dagger B give you like Z squared. So when you combine the conservation law, you're seeing that the total charge is conserved, the dipole in X and Y is conserved, and the shape of the quadrupole is conserved. So it's the same global charge, the same conservation law as the symmetric, J-less symmetric and Sergej theory introduced by Fractional. Okay. So now I tell you the field theory derivation for the another way to derive the same thing. So the first equation is nothing but is a continuity equation. That's the conservation of charge. The second equation is nothing but it's conservation of momentum. So M multiplied by the current equal to the momentum density so the derivative of shape tensor is exert a force on the element, and here is the external force, the Lorentz force. So the second equation is just the conservation of the momentum. Now again we go to the lowest lambda level limit. Ignore this term. So basically from this you think that the current can be obtained from the shape tensor with the explicit form. And this current can be like after you calculate the current in terms of shape tensor, you plug it back to the upper equation. You have the following form, such that the Jij is nothing but written in terms of shape tensor. It's very straightforward to show this conservation. And because of this explicit form, the Jii here is the J is also 0 by just explicit calculation. So here I show you like using the field theory to show that we have the symmetry that we expect. And what is the consequence of that? The consequence is that in the fractional quantum Hall, some excitation has a fractonic behavior. So basically, the quasi-particle and quasi-Hall are charged, and because it's head charged, and then it is fractal. Another excitation is yeah, if you do not apply electric field, because in this equation I do not have the electric field term in that. If we only have the magnetic field, then the anion will not move freely. Another excitation is a composite fermion. When the Filling fraction is like 1/2 or 1/4, then you have the semi-liquid state. And then in this case, the composite fermion have a charge neutral, but it has the dipole moment. Because of the fractonic behavior, like the dipole can only move perpendicular to this dipole moment. So basically, it's a composite fermion have the momentum perpendicular to the dipole moment of the composite fermion. So this result is known in the literature, but here I show you how to derive this using the symmetric and Sergej. Yes. Right. Interaction doesn't matter. Is this Nguyen this? Yeah. So if I only consider the dynamic of excitation without the electric field. Yeah, it's next chapter. Right, right. You still have the combination, right? Because electric field will multiply by the density of rho. Then with electric field here, you can do that. But I don't have, at the end, I do not get this equation. Yeah. So in the similar way, when you consider the 1D boson, if you do not have electric field, then there is no dipole symmetry. If you apply very strong magnetic field, it have dipole symmetry because boson need to go like opposite direction to conserve the energy. If apply electric field, then boson need to move opposite direction. So the total dipole moment has to be conserved. So electric field can change the photonic behavior. Another excitation is called the graviton excitation in fractional quantum Hall. At the small momentum, it is a quadruple. And so the magnetoton excitation or the graviton excitation is really to move because it's a quadruple. There's no restriction on that. So now I'm trying to show that the thing called the projected U1 case. That's is the symmetry in the lowest Landau level. Yeah, I think I don't need to introduce them again. So here I have the A and A dagger. It's a raising and lowering the Landau operator. B and B dagger are the magnetic translation operator that I introduced before. So if you consider the operator like B dagger power of n plus 1 and B power n plus 1, they are the generator of the thing called the W infinity algebra. So with a commutation relation like that, you can create exactly using the commutation of B and B dagger. And the W infinity is I have the infinite number of generator, and it's a global symmetry of the free Hamiltonian in the low Landau level limit. If you do not consider the interaction between electrons, then W infinity is a global symmetry of the free Hamiltonian if the infinite number of generator. So now let me consider the lowest Landau level field operator. So with this, this wave function satisfies the lowest Landau level constraint at in T, like introduced yesterday. We have the following form in the symmetry case. So we can write down the projected lowest Landau level projected field theory operator with this form. The wave function, and A is the creation, is the annihilation operator with the harmonic statistic like that. So with the anti-commutation relation of the lowest Landau level electron field, you can have the lowest Landau level Dirac delta function. So if you have no like lowest Landau level constraint, then basically the commutation relation of the anti-commutation relation of fragment field should give you the delta function. But here we have something not delta function. It's a smear of delta function because of the non-commutative property of the lowest Landau level constraint. So we can use this like delta function to project any operator to the like single particle operator to the lowest Landau level. So here G is any function, but we can integrate out with the lowest Landau level delta function like that. This result will satisfy the lowest Landau level constraint. So here I have some like useful relations that to be complete. We will use it later, but we don't need to remember. So you use this like lowest Landau level delta function to the lowest Landau level projector. So you integrate any function G with the lowest Landau level delta function to get a new function such that satisfies the lowest Landau level constraint. Any function. Yeah, it's D and Z bar. But then when you integrate with the lowest Landau level delta function, you satisfy the constraint, lowest Landau level constraint. You can so use two different ways to satisfy this. You calculate again the delta function. So the delta function here is explicitly in the symmetric way. You can choose different ways to calculate this. And then it always satisfies this one. Here, yeah, there's some breakdown that we use later on, but not important. So if we consider the unprojected U1 transformation, so the transformation of the field is the sum I multiplied by some function multiplied by the field. So this thing is nothing but is a U1 J transformation, local transformation. But for sure, this thing it doesn't satisfy the lowest Landau level. So that means the unprojected U1 transformation violates the lowest Landau level constraint. You can fix this by introduce the projected U1 transformation. So you have the transformation, you use a delta function like lowest Landau level delta function to project it to the lowest Landau level. And from the useful relation that we had before, we can show that the lowest Landau level U1, the projected U1 transformation has the following form. And here is some kind of like anti-normal order being B dagger we saw before. So yeah, we can obtain from any function by repeated Z by B dagger and Z bar by B. And after that, we do the anti-normal order. Okay. So here is like with any function, we can write down the operator of this transformation of the projected U1 transformation with any function. So rho L here is nothing but it's the density in the lowest Landau level. So we can show that with this explicit form, when you commute with the psi, you will get back to this result. So this operator acting as generator of the projected U1. In the same way, when you consider the usual ENM, the density operator is also the operator that is global at the local U1 transformation for the fragment field. And then we can show that similar with did before, we can show that the commutation relation of the density operator with different psi can be mapped to another operator, such that the bracket inside is a Moyer bracket with this one with a lot of derivatives. So we call this Chart density algebra. That's come from the density of the commutation relation of the density operator at the lowest Landau level. And it's also the generator of the projected U1. So here now, if you choose C with this form, explicit form, this exponential I Ux, then the Chart density algebra gives you nothing but it's the GMP algebra, which is a commutation relation of the density operator in the lowest Landau level. And now if you choose the C with this explicit form, then the Chart density algebra from this equation gives you nothing but the W infinity algebra. So W infinity algebra and the GMP algebra are the same. Yeah, this is a different representation. So now I can argue that area-persevering is a long wavelength limit of W infinity. It is quite trivial to solve. So remember the definition of Z and Z bar has the following form. So dZ is nothing but is a magnetic length multiplied by momentum. So in the long wavelength limit, when you take the K momentum multiplied magnetic length is very small compared to 1. The Chart density algebra reduced to the area-preserving algebra. So the area-preserving is nothing but it's a long wavelength limit of check algebra, check density algebra on the ZMP algebra. And in this case, rho C is nothing but it's a generator of area-preserving diff. Right. So, as I mentioned, the lowest Landau level projected U1 and W infinity, it is the only symmetry of the lowest Landau level for the free Hamiltonian in the flat background, A naught equal to 0 and Gij equal to delta Ij. Now, if we consider the interacting lowest Landau level Lagrangian, so in the lowest Landau level, we ignore the kinetic energy. So only the coupling with the action of potential, and here is the interaction, the density interaction, but both of them are lowest Landau level. So the question is, can we think of the lowest Landau level projected U1 as a gauge symmetry of this Lagrangian? It's a long wavelength limit. So is area-preserving diff is a symmetry of this problem. And so we do the following thing. We do the area-preserving diff in the passive way. So here with the generator, with this generator, we see that the transformation of the density under the area preserved, the U1 projected transformation. With this generator, we can calculate the chain of the density. And you can also calculate the chain of the cosine for sure. So the transformation of this action have two terms. The first line comes from the first two terms. The second line comes from the interaction. We know how the density transform result. Do the integral by part and see the full transformation of the action. So now the first line here can be compensated if you also use the transformation of the background A. So the A naught row here, you just do the transformation of the A naught. It can compensate with the transformation of the cosine row. So the first line you see that it has the same form as the area-preserving diff, the nonlinear version that I showed you before. Second of all, if you consider the rotational symmetry potential, the short range, such that the potential with the following form, you can write the distance, and you can written in terms of this form, the matrix multiplied by the difference in the coordinate is the distance with a measure. So the second line here can be compensated if you also make the chain of the matrix. So this thing is nothing, but it's see that it's the same as the area-preserving diff of the matrix that I introduced before. So that means this action is invariant under the area-preserving diff of the background and the projected U1 of the matter field. So now we recover the nonlinear area-preserving diff of the background field and is invariant of the action. However, it's not a symmetry. It is not a symmetry. The reason because on the flat background, the global symmetry of the action is only the symmetry if we choose the killing vector such that makes the background intact. So if you train both the matter field and the background, we call the passive diffeomorphism, which always the invariant of the action, if you write the action properly. However, if you have the transformation that makes the background intact, it is a symmetry. Okay. And the C that satisfies this is that have the explicitly following form. So the first thing is a global U1 symmetry. The second term, it comes from the global magnetic translation. And the last term is a global magnetic rotation. So basically from the projected U1 and the Area-persevering disk, I recover again only the symmetry of the interacting problem is 3 of them. And there are the subgroup of lowest Landau level projected U1. So how about the other generator? We can extend this to like more complicated function. And actually, like other generator will generate excitation. And here you have x squared, y squared. But if you have the C equal to ZZ, C equal to Z bar, Z bar. It's not x squared plus y squared. This one will create the current graviton. And this one will create the also current graviton with different currency. So what I believe is that the lowest Landau level projected U1 will generate the low energy manifold of the fractional quantum Hall problem. On top of this symmetry, as a generator will increase excitation in the low energy excitation, and the spin begin from 2 to infinity. So basically, the fractional quantum Hall is a place that we can see the higher spin dynamic. And we also can derive this higher spin dynamic using the composite fermion, but it's consistent with what we understand over here. So here I show you again the Chern-Simon theory, I mean the linear version in the Chern-Simon for the fractional quantum Hall, like the high rank symmetry. So yeah, with this magnetic field, like you rewrite it in terms of the perturbation of the matrix, you see this following form. So this term, it's a full Chern-Simon term, but you can separate it by 2. So here you have the A0 multiplied by the curvature is calculated from the perturbation of the matrix. So this term tells you that when you variation this term with respect to A0, you get some charge density. It tells you that when you put the quantum Hall on a curved space, the charge density will change by the curvature. So that is nothing but it's a Wenzel shift. When you put the quantum Hall on sphere, the total number of charge will change by the Euler characteristic of the sphere. And the second term is the response of the action with respect to the matrix. And this is nothing but it's a whole viscosity. So because of the high rank symmetry, these 2 terms come together. So it tells you that the Wenzel shift, the coefficient of Wenzel shift, also is a coefficient of the whole viscosity. So it's a constraint. And this thing is nothing but is a Wenzel term in fractional quantum Hall. So, right. So this thing is the Wenzel shift and this thing is the whole viscosity. So the high rank symmetry provides a relation between the Wenzel shift and the whole viscosity. It's thus constrained by symmetry. And I think that's our time. So here is a summary. So the nonlinear high rank symmetry in the lowest Landau level is nothing but it's area-persevering deep when you go to a long wavelength limit. So the factonic behavior of excitation in fractional quantum hole is a consequence of the high rank symmetry. And with the same formalism, we can study the volume preserving has a high rank symmetry in 3+1. And we have the multiple conservation of the skyrmion and theta. And the non-commutative U1 is also nothing but it's the area-preserving deep, which I also do not have time to discuss. Thank you.
All the fields kind of show with A, like A and rho, they're external.
External field.
Dynamical, like kind of probes.
The both field, but basically you see that this action. So this action for psi is a matter field.
Yeah.
So this transformation is a transformation if you only transform for psi. And now if you also transform A and transform G, you make the relation of action equal to 0. Okay, and then my point here is that this thing, if I consider the transformation acting on matter field, with any C, I can have the area-preserving transformation acting on the matter field. And this creates excitation if it's not a symmetry. So with this one, if you acting on ground state, it preserves the ground state, but you add this extra term. This thing acting on ground state increases the graviton with the spin 2. ZZ will be spin -2 and ZZ bar. Oh. Yes. Right.
And the actual representation is a group of space.
Right.
And it depends crucially on the factor. If you have factor 1, there's only one state in the top space with factor 1.
Right.
So it's the representation. If you have a fractional filling, you're going to have
exactly.
So how for the representations classified and how the factor appears the question of classification of the possibility.
So exactly. So the thing is that you consider the ground state and you consider the fractional quantum hole, not integer quantum hole. You deform the ground state like you deform all particle the same way you do. This will lead you to the low energy manifold of the Fock space. Okay, and then you can write down the thing called the geometric action. You have the area-preserving as a group. You write down the geometric action, and the geometric action have the form of like KPA plus. So this thing is one form, but the algebra is the area-preserving algebra, and K here is the same as the Chern-Simon of the ring function. This contact, yeah, right. So for Laplace state, K is nothing but filling fraction, 1 over K. We have the K. Yes. Because with the fractional quantum Hall states, topological coefficient we know. So basically, we can cook up the geometric action for, and furthermore, the area-persevering have many generators, and as I tell you, like the zero spin, like the Bolo one is the symmetry. The spin one, the translation is also the symmetry. But begin with spin two with the excitation. And then you can have the excitation like 3, 4, etc. And it's inside yeah. So basically the dynamic of the lowest lambda level is higher spin theory, begin from 2. Yeah, it's not in the, yeah. It keeps the excitation, yeah, right. Then, yeah. But you're saying that in like, if you write down any field theory properly, you need to have the thing called the passive Diffeomorphism invariant. So tells that you can change the coordinate without changing it. Is a different way to choose the coordinate. So the different way to choose the coordinate is the same as you change both the matter field and the background. So the active transformation gives you the symmetry, which it tells that you just change the matter field, but you do not change the background. So you need to have something like killing vector such that doesn't change the background to have the symmetry. Because if you transform both the matter field and the background, then basically you can make the theory invariant. Because it's nothing but it's a change the way you label the coordinate. But if you have the active Diffeomorphism transformation, that means you have the symmetry. Because that's something like doesn't change the background. What is the symmetry of the problem? Okay.
So now, this is a symmetry, but the fact that we have it any go higher forces you to have all the citations for the highest.
No, I think that what I view of this is that it is the following thing. If you do not consider the interaction, like free Hamiltonian, then the full of this is a symmetry.
Imagine it's direct.
So with interaction, I'm saying that I'm thinking of this the full group of area-persevering is the thing that creates a low energy manifold. It's not the full Fock space, because this area-persevering, you deform all electron is the same way. You do not like put electron there and keep that same. You deform the full is the same way because the electron interact with each other. I expect that it will go to the like low energy manifold rather than with something, yeah.
At this lowest level,
yeah.
Property for problem, the presence of interaction forces.
Yeah, excitation.
Spins.
Right.
Sure.
Right.
There's something that one can say about the half-field Landau level.
Half-field Landau level, yeah. The Galilei state, I tell you that here. Right. So when you have the half filling, then you have the Fermi state, and then because of the high rank symmetry, the composite fermion can only move perpendicular to this type of moment. Is a consequence. And I think that like people do fractional quantum Hall, they know this like long ago. They know how the composite fermion move, like it perpendicular to the dipole moment. But yeah, I saw that we can derive this using the high rank symmetry argument.